Let's jump right into this explainer. Welcome. So today we're exploring how chemistry is way, way more than just memorizing a bunch of formulas in some dusty textbook. It's actually this incredibly dynamic, living language that lets us read the physical world all around us. We're going to trace the journey from those tiny, invisible particles making up our universe right to the very visible, massive impacts they have on our everyday lives.
We're kicking our journey off today not in some fancy high-tech lab, but with a high school student named Maya. Picture this. She's sitting in a super quiet science classroom, just staring in total frustration at her chemistry test. At the very top of the page, right next to a diagram of two metal strips in separate beakers, her teacher, Mrs. Bell, has left one little note in blue ink: check the direction of electron flow. Now Maya knew something was moving in that diagram, but under the pressure of the test, she literally drew the arrows pointing the wrong way. That one single phrase, check the direction of electron flow, is the core mystery we're unraveling today.
Seeing Maya's absolute frustration, Ms. Bell decides to just step away from the paper diagrams altogether. She pulls out real glass beakers, a strip of zinc, a strip of copper, and a wire, and she builds a real-life Daniel cell right there on the lab bench. But just as she hooks it up to a tiny bulb, the storm outside completely knocks the power out. The entire school plunges into total darkness. Suddenly, it's just the sound of the rain and the glow of one tiny amber bulb sitting right there on the desk. Section 1. The battery after rain. Finding light in the dark.
Now that tiny little bulb is being powered by an entire invisible world of moving particles, specifically two connected processes. First, we have oxidation, which is the loss of electrons. And then we have reduction, which is the gain of electrons. Now these aren't two separate events, right? They're literally two sides of the exact same electron transfer coin. You simply cannot have one without the other. Basically, if one substance loses electrons, another absolutely must be there to catch them.
Section 2. The dance of electrons. The science of the spark.
Okay, so to truly understand the exact mechanics of this spark, we're going to use a really foundational memory trick: oil rig. That stands for oxidation is loss, reduction is gain. It tracks exactly how these invisible, negatively charged electrons are behaving during a reaction. So, whenever you're trying to figure out what the heck is happening in a chemical system, oil rig is your mental shortcut for tracking all that electron flow. It's a real game changer. And here is how the whole shebang comes together into a complete circuit. In our Daniel cell, the zinc acts as the anode, and since it's more easily oxidized, it loses electrons. Those electrons bypass the water entirely, they travel through the external wire, which by the way is what creates our electric current, and they land right at the copper cathode. All the while, a salt bridge is allowing ions to flow, which perfectly balances out the electrical charges. It's a beautiful, fully interconnected system. To really grasp the sheer, breathtaking scale of this invisible world, you have to consider Avogadro's constant. That's 6.02 times 10 to the 23rd power. I mean, wow. In just a single mole of a substance, you have an incomprehensible swarm of atoms and electrons constantly interacting to shape reality. We're not talking about a few dozen particles here, folks. We're talking about a scale that literally dictates the rules of our physical universe.
Moving on to Section 3. Chemistry in everyday life. Scaling up from the classroom.
Think about it. If a totally microscopic electron transfer can power a light bulb, just imagine its macro impact. Chemistry is pretty much the invisible architect of our modern world. I mean, it adjusts the pH and removes dissolved minerals in our drinking water just to keep us safe. It halts unwanted oxidation in our food. And it builds the complex polymers found in literally everything, from flexible medical gloves to rigid bicycle frames.
Take food preservation, for instance. It's fundamentally a battle against unwanted chemical reactions. It's actually the exact same oxidation happening in our battery. But in food, the oxidation of fats and oils produces those stale, really unpleasant flavors. So we rely on strategic chemistry, using things like antioxidants and specific temperature controls to actively slow down these enzymatic and oxygen-driven changes.
And you know, this exact same foundational logic applies straight to material science too. Think of polymers almost like interlocking chain links. They're built from these smaller repeating units called monomers. By tweaking exactly which atoms are used, how long the chains are, and how they cross-link, that exact same underlying chemistry creates a plastic water bottle, a scratch-resistant phone screen, and yup, even the DNA in our very own bodies. Section 4. A sustainable future. Energy, environment, and our choices. So,
We've seen the incredible power of chemistry, which brings us to a massive, absolutely crucial question. How do we actually build a sustainable future? Because the reality is, every high-performance battery, or brand new polymer, requires mining, manufacturing, energy, and eventually disposal. We're constantly forced to balance this incredible technological progress with the harsh environmental realities of resource depletion and pollution.
Balancing all this? Well, it requires a seriously multi-layered approach. It means radically improving battery chemistry so we can store renewable electricity way more efficiently. It means reducing wasted energy across the board, and honestly, it involves fundamentally shifting how we design products in the first place, creating things that are actually meant for repair and recycling rather than just sending them straight to a landfill.
What sustainable chemistry really does is it changes the timeline of how we think. It forces us to consider a product's entire life cycle, its eventual disposal, its environmental footprint, its byproducts, long before it's ever even manufactured. It's about asking the hard questions before a product is made, rather than just reacting after problems suddenly start appearing in our water or our air.
Section 5. Reading the Invisible World, Maya's Epiphany.
Back to Maya, sitting in that darkened classroom, watching that single bulb glow. The Daniel cell finally makes sense to her. She realizes that a battery isn't just some diagram you memorize for a test. It's a live working system where every single part makes the next part possible. Chemistry is a foundational language. It's a tool that empowers us to look beneath the surface. Understanding ions and electrons isn't just about memorizing, it's about gaining the solid evidence we need to make wiser decisions for our world.
Maya ultimately added this incredibly profound thought to a science program application. She wrote, "Evidence does not always appear as something you can see directly. Sometimes it appears in what changes because of it." And as you go about your day today, I challenge you to look a little closer. What microscopic dances of electrons are shaping the world right in front of your very eyes? Thanks for joining me on this explainer, and definitely keep questioning the invisible world around you.